So in this video, we will look at this quantity called angular momentum. And just like the rotational kinematics and the idea of torque and angular acceleration, we'll see that there's analogies between this quantity of angular momentum and the linear momentum that we talked about earlier in this quarter. So to define angular momentum, we consider an object that's rotating around an axis. So here I have the disk. It's rotating counterclockwise around an axis that goes through the middle. And as it's rotating, it has this quantity, which we call angular momentum, or angular inertia, I guess is the way that you can think of it as well. So it's rotating around, and we have this quantity, so we'll call this L. Angular momentum is L. And this L, well, if you remember, linear momentum is mass times velocity. And so in rotational equations, you would notice that we replace mass with rotational inertia, and we replace velocity, or this linear velocity, with omega, angular velocity. So the definition of angular momentum is L, which is angular momentum. Is equal to I, so this is my rotational inertia, times omega, which is my angular velocity, and this will be in radians per second. Okay, so yeah, omega needs to be radians per second, and that's really all there is, guys. Okay, as far as defining the magnitude of angular momentum, you just take the moment of inertia, or whatever is spinning, you multiply it by its angular velocity, and you'll get the angular momentum. But notice that there's this little arrow here, this little vector arrow, and angular momentum has a direction. And it's going to be in the same direction as the angular velocity. We haven't talked about the direction of angular velocity, and it's kind of tricky because the angular velocity, it's going around in a circle, right? And so physicists have devised a way to define the direction of these rotating quantities. And the way we do that is by something called the right-hand rule. So once again, we have this disk, it's rotating counterclockwise, and we need to find the direction of the angular velocity, which in turn would be the direction of the angular momentum. So for this, we use the right-hand rule. So this is say this is your right hand. Your fingers will curl in the direction of rotation. Okay, so since it's rotating counterclockwise as we're looking from the top, you imagine kind of like a pole or something goes through the axis of rotation, and your fingers wrap around in the direction that's rotating. And then you stick your thumb up, and the direction of your thumb is going to be the direction of your angular velocity. So in this case, since it's rotating counterclockwise, your fingers on your right hand would wrap around this way. You can try this. I encourage you to try this. So your fingers wrap around this way, your thumb sticks up, and it turns out that the direction of your angular velocity is pointing up. And this is going to be the same direction as your angular momentum. So angular velocity and angular momentum do have a direction. That direction, the vector, always points along the axis of rotation, and the direction that it points is determined using the right-hand rule. Okay, so again, fingers curve in the direction of rotation, point your thumb up, the direction your thumb's pointing is the direction of the angular velocity and angular momentum. If you have trouble visualizing this, again, I encourage you guys, use like a pen or pencil or something for your axis and literally like grab that, wrap your fingers around the axis in the direction of rotation, grab it, and then point your thumb, and that'll be the direction that you need. Now, just like linear momentum, angular momentum is conserved. So this is a conservation law. It's a very powerful conservation law, and it's stated here in the text. So in the absence of external torque, and I emphasize the external here, you can have torques internal to your system, but if you do, it may change the momentum of things within that system, the angular momentum of things within that system, but the angular momentum of the system as a whole will remain the same. Just like when we were doing collisions, we had two objects collide, they could change, each one of them individually could change their momentum, but when we looked at the sum of the momentum of the two, they always had to equal the same number in the absence of an external force or external impulse. In this case, the angular momentum of my whole system will be the same as long as I don't have an external torque. So I don't have an external force acting some distance away from your pivot. So to illustrate this, we imagine once again we have this disk and it's rotating counterclockwise, and then I drop another disk on top of it. So say that this disk has mass m and this disk is mass m, and I, for a rotating disk, will be 1/2 m r squared. So just assume that they have the same r value. So our angular momentum before would have simply been 1/2 m r squared. So this is our I times whatever the omega was that this had before. Okay, so I'm going to call this omega initial. And maybe the question is, what's the final omega? Okay, so after this gets dropped down, what's the final omega going to be? Well, we know that the angular momentum before has to equal the angular momentum after. And so before, only this was rotating, this wasn't rotating yet, but once they drop, because of friction, there will be rotation. Yes, friction will exert torque on this, but it's internal to our system. And so I would say 1/2 m r squared will be equal to, well, when these are combined, it'll have twice the mass. Okay. I'm sorry, I forgot my omega there. Oh my goodness. Sorry guys, I gotta restart this again. Slideshow, do from beginning. Just bear with me here. Okay, so there's an omega here. Okay, so this is the omega naught, and then that has to equal the momentum after. Well, after it'll still be 1/2 mr squared for the moment of inertia, but now I have 2m. Okay, I have twice the mass of the disk. They both have the same radius, so my r squared is going to be the same. And this will be omega final. Maybe we want to solve for this. And so we cross a bunch of stuff out. R squared is out. So what we're going to find is that omega final will be essentially, oh my goodness, will be 1/2 of omega initial. I think it's my pen that's doing this, guys. Okay, so divide this 2 by both sides, we get 1/2 omega initial. Okay, so this is a very simplistic example, obviously, but it gives you the idea. Okay, we use this idea of before and after once again, and we can solve for things like, hey, what's the new angular velocity? Tomorrow, or I shouldn't say tomorrow, but next class that I see you, I'll show you some really, really neat demonstrations that make use of this idea of conservation of angular momentum and angular momentum in general. So I hope you guys are looking forward to that, and I will talk to you then.